Good morning all. Last week we have studied about RTOS and kernel. Today we will discussing about process management in an RTOS. These are the topic which we will cover in this session. Initially I will going to discuss about process management. Then I will move on to various process management techniques such as process creation, process termination, process synchronization. And we will discuss each topic in detail later in this session. Here we are going through process management. We know that in a computer system, a program in execution is called a process. And during the execution of the process may need multiple resources. And these resources are allocated using the process management activity inside the kernel. And after completion of the process, the allocated resources should be deallocated. And during the execution of the process may need to communicate with each other. So this communication, this allocation and deallocation of the resources is achieved using the process management activity. So we can say the process management includes allocation of the resources to a process and deallocate resource after completion of the process and allow process to share information, and this is done by inter-process communication techniques. Then prevent the unauthorized use of resources and providing synchronization among processes. And this synchronization is achieved using the context switching and process scheduling activities. Here you can see the state diagram of a process. And inside this state diagram, there are multiple states such as new state, ready state, waiting state, running state and terminated state. Depending on the status of the process can be in any of these states, either new, ready, waiting, running or in terminated state. Suppose if the process is just being created, then the state of the process will be in new state. And if the process is completed execution, then it will be in terminated state. So here new and terminated state are two endpoints of a state diagram. And all the process should go through these two states, this new state and this terminated state. Between this new state and terminated state, the process can go through ready state, running state and waiting state. If the process is currently being executed by the CPU, then the state of the process is called as running state. During the execution of the process, if the process calls some exit instruction, then the state of the process will be switched to terminated state. And during the execution, if the process requested some IO resources, then the state of the process will go to waiting state. So at the waiting state, the process is waiting for some IO resources, and if the IO resources become available, it will go to ready state. So in the ready state, the process has all the resources required for the execution, but the CPU is executing some other instruction, so it cannot execute currently. So it is waiting for execution. Such time the state of the process is called ready state. And you can find multiple processes which is waiting for execution in this ready state. And a scheduler will allocate one process to the CPU for execution. And during the execution, the process of the state of the process will go to running state. We know that a process management consists of process creation, process deletion and communication and synchronization. Now we are moving on to process creation steps. All the process is identified by a process ID and it is unique to all the process in the system. So the process creation step include creating a unique ID for process identification and allocating various memory resources. So we can say that during the process creation, a unique process identifier is generated and insert a new entry in the primary process table. So this primary process table contains all the process present in the system. So during the process creation time, a unique process identifier is generated and insert into the primary process table. After that, the required memory segments are allocated for the process. The first one is the process related memory segments. It includes allocate memory for the program execution and allocate memory for the process control block. And after allocating the necessary memory locations, the various memory should be initialized. Here in the case of a process creation, the PCB block or process control block initialization also required for the process creation steps. Here you can see the life cycle of a process. Initially, the parent process is executing, and during the execution, the parent process called a fork function or a system call, and this will create a child process, and this child process is started executing, and after execution, the child process called exit statement. It means that it wants to terminate, and during that time, parent's execution completed and it is waiting for child to exit, and child is exiting using the exit system call. After the parent will resume operation. This is simple life cycle of a process in a Linux or Linux based operating system. Here you can see a tree of process in a typical Linux system. Here in this system, you can see the parent of all the process is the init, and it has a process ID of 1, and it has multiple childs such as login process, kthread process, and sshd process, and each has different process ID, and all these child process has again subchild like khelper, pdflush or bash process, etc. And this child also can have another child like ps, emacs, etc. And in this case, the process ID of every process should be unique, and each process can be identified using this unique process ID. And in a Linux system, the parent of the all process is init, and it has a process ID of 1, and all other processes are the child process of this init process. A process can create a child process using fork system call, and the resources required for the child process is obtained from parent process or from operating system. And after creation of this child process, the parent process will continue its execution along with the child process. And before terminating the parent process will wait for all of its child process to terminate. And after terminating all of its child process, parent process will exit. So we can say that when a process creates a child process, that child may obtain the resources from operating system or parent processes. And when a process creates a new process, the parent process continues to execute concurrently with its children, and parent process wait until some or all of its children have terminated. Here you can see the memory layout of a process, and the memory layout starts with the test segment, then data segment, then heap segment, and finally the stack segment. And this test segment contains the programs of the process. So we can say that test segment, also known as code segment or simply test, and is one of the section for program in an object file or in memory which contain executable instruction. So the CPU is utilizing the program stored in the test segment to execute the process. And after test segment, the next segment is the data segment, and the data segment contains all the initialized data inside the program. And next come BSS, and BSS contain all the uninitialized data. After BSS, next is the heap segment, and this heap segment is used to store dynamic memory allocated values. So using in C or C++ language, we can use calloc and malloc functions to create dynamic memory locations. And after heap location, the next one is the stack segment. This stack segment is used to store variables, and it is unlike all other sections. The stack is growing downwards. All other sections are growing upwards. In a process creation, along with the memory initialization, process control block is also need to be initialized. And this process control block contain all the information necessary for managing a process. So it contain process ID, process state, process priority, accounting information, program counter, CPU registers, and process control block pointers. Here the process ID is unique to every process, and the first value of the process control block is the process ID, and it is unique to every process. Then it's come process state, and this process state indicate context information of a process. And next one is the process priority, and it is used by the process scheduler, and using this priority, the scheduler assign task to the CPU. And then it is the accounting information, and it is used for billing purpose and performance measurement. Then it also contains program counter, CPU registers, and PCB pointers. And along with that, the process status also present in the process control block, and this process status indicate whether the process is in ready state, running state, blocked state, etc. We are moving on to process termination or process deletion stage. We know that when a process is created, there is multiple resources are allocated to the process. This include memory and various IO resources. So after termination of the process, all these resources should be deallocated, and this is happening during the process termination or process deletion stage of the process. So we can say that when a process terminates, its resources are returned to the system. It's purged from any system list or tables, and its process control block is erased. PCB memory space is returned to a free memory pool. All of the system resources are freed up. Open files are flushed and closed, etc. And after termination of the process, we will get a return status, and this return status should be communicated to the parent process. And if the parent process is not present, then it has to be communicated with the init, and it is the init process is the parent of all the process. So we can say that process termination status and execution times are returned to the parent if the parent is waiting for the child to terminate, or eventually return to the init if the process become an orphan. A process can be terminated in multiple ways. It can be terminated in normal way, or it can terminated abnormally, or sometimes the parent may terminate the execution of its children, or sometimes the process may be terminated by the operating system. In the normal means of exit, the process will call the exit system call, and this exit system call is called when the process completed all of its task, or the process completed its purpose. Upon receiving the exit system call, the operating system will deallocate all the resources which is allocated to the process and exit the process in a graceful fashion. And a second method of the process termination is the abnormal termination method. Here, due to some program errors or runtime error or input-output error or user intervention, the operating system will terminate the process forcefully. And sometimes the parent process may terminate the child process, and this may be happen due to child has exceeded its usage of some of its resources, or task assigned to the child is no longer required, or parent is exiting. Such times parent may terminate the execution of the child process, and sometimes the operating system may terminate the process forcefully. This may be due to shutting down of the operating system, like that. Context switching. In a multitasking system, multiple processes can be executed in a single CPU in a time-shared basis. It means that in a multitasking system, multiple processes are waiting to be executed, but there is only single CPU is available to execute the processes. So the CPU scheduler will assign a single process in the waiting process list to the CPU, and this process will be executed at a particular time, and each process executing process will allocate a time duration to execute, and after expiration of this time duration the process will stop, and it allows another process to execute in the CPU. So here there is one stopping of one process and starting of another process. So overall this method is called context switching. So we can say that the stopping of one process and starting of another process is called context switch, and it allows multiple processes to share single CPU, and it is an essential feature of a multitasking operating system, and it is computationally intensive because we have to store all the CPU state of the stopping process, and we have to restore all the CPU state of the newly executed process. So it is more computationally intensive than any other situations, and a context switching is triggered by multitasking, interrupt handling, and kernel and user mode switching. Here you can see the timing diagram of context switching. In this timing diagram there are two processes, process P0 and process P1. Initially the process P0 is executing, and during the execution, due to some reason, the process P1 wanted to execute. So there is a context switching happened. This context switching involves saving of state of process P0. The first step of the context switching is the saving of the various CPU state of the process P0. After saving the CPU state of the process P0, then we need to restore the state of process P1. So after these two tasks, the process P1 can execute, and after some time again process P0 want to execute. During that time all the execution state of the P1 should be saved in the process control block. After that all the state of the P0 which is saved in the process control block should be reloaded into the CPU, and after reloading all the state of the process P0 into the CPU, the process P0 can execute. Here you can see about process scheduling. In a multitasking operating system, you can find multiple processes, and each processes need to be executed in the CPU. But the CPU can execute only one process at a time. So all these processes will be waiting in a ready queue for execution. And the process scheduler inside the operating system will assign any one of the processes to the CPU. and the assignment is done based on the priority of the processes. So we can say that process scheduling is an activity of the process manager that handles the removal of a running process from the CPU and selection of another process on the basis of a particular strategy. And this strategy is called as process scheduling algorithm. And these are the goals of process scheduling. The first one is the better utilization of CPU. It means that we can run multiple processes in a time-shared manner and increase the throughput and reduce waitage time and minimize response time and prioritization of the process. These are the goals of a process scheduling. Here you can see the functional diagram of a process scheduling. In this functional diagram, there is one CPU, and inside the CPU all the processes are executed, and this CPU can execute only one process at a time. And we can see multiple processes which is waiting in this ready queue for execution. So in this ready queue there will be multiple processes, and the process scheduler will select any of this process from the ready queue and assign to the CPU for execution. And the scheduler selection is based on the priority of the processes which is waiting in the ready queue. And during the execution of a process, if some IO request happen, then the process will go to the IO queue. And when the IO devices or IO resources become available, it will again goes to the ready queue and wait for CPU. And if the time slice given to the process is expired, it means that each process will be allocated a time duration for CPU execution. And if the time duration is expired, then it will also go back to the ready queue and wait for execution. Or if the process create a child process, during that time child will execute and the parent process goes to ready queue and wait for execution. Or if an interrupt come, then the interrupt will be executed. The meantime the original process will goes to ready queue and wait for execution. So after when the CPU become available, the scheduler will select one process from the ready queue and assign to the CPU for execution. So this is the functional diagram of the process scheduling. Here you can see some of the algorithms of process scheduling. The first one is first come first serve algorithm. In the first one, first served algorithm, you can consider the ready queue, and the process first entered into the ready queue will be executed first, and the last entered into the ready queue will be executed last. And the second algorithm is the earliest deadline first algorithm, and this algorithm select the process with the earliest deadline and it is allocated to the CPU for execution. And the next one is shortest remaining time first, and next one is the round robin scheduling, and then fixed priority preemptive scheduling. In fixed priority preemptive scheduling, each process is assigned a priority, and depending on the priority of the process will be allotted to the CPU for execution. So far we have studied about process management. This process management includes allocation of resources to the process when the process is created, and deallocation of the process resources when the process is terminated. And during the process execution time, sometimes process may need to communicate with each other. So the inter-process communication is also part of this process management activity. And along with this inter-process communication, the process synchronization is also required, and it is also part of process management activity. And in the process synchronization, it comes context switching and process scheduling. So I am winding up this session. Thank you for listening. Bye.